Hello, gang. We're back for lesson 5.3. Kind of a daunting title, Solving Unsolvable Equations. That sounds like a little bit of a paradox, but we'll see that they're both unsolvable, yet still solvable. So the 3-minute review, though, is straight from the last day's stuff, or 2 days ago, or whenever a days ago, where we want to graph a function. This function, we don't know how to graph it. But what we do know is we can graph the pieces, right? So I'm going to graph the pieces. Um, I'm going to graph y equals log base 2 of x. And I'm also going to graph y equals x. And then what I'm going to do, I'm going to find the sum function. And that's the whole plan here. This complicated function, I don't know. But if I break it into its pieces, and then use some skills from before, I'm okay. So uh, y equals x is a line with, should have some scale on here, I suppose, 2, 2, right up the middle, there's the line y equals x. Log base 2 of x, remember, has a 0 at right there, and then 2, 1, and in fact, because base 2 is so little, I can actually get a couple more points. I can get that point there, which is 4, 2, right? When x is 4, the log base 2 of 4 is 2. And also, of course, the negative I want there, half is negative 1, right? And there's my two pieces. Well, what do I do? I can add these together, right? Now, you should be using a ruler for your line, of course. I'm trying to save a little bit of time. Add them together, right? So for each point along the x-axis, I sort of add the pieces together. So it's red plus blue, 0 plus 1. 1 plus 2 is 3. Whatever this is plus whatever this is. And again, I can just stack it on top. 2 and 4 is 6. Interesting is down here somewhere. So for instance, this one, this half and, what would that be? Half and negative 1, and this is a half and a half, right? Y equals x is just a half and a half, so this is down here somewhere, right? And then I can get an idea of what this function looks like. This is f of x. Also, it asked me to state some stuff. Well, what sorts of stuff would you like me to state? The domain. Well, we talked to some detail in the last couple of days of when I had two functions, what's the domain and what's the range? Well, the domain, remember, is you have to be defined in the combination function, you have to be defined in both. And I can see from the graph, this green graph is defined only for x is greater than 0. Notice this domain was x is greater than 0. This is all real numbers, but when I want to find what values are in both, this is the winner right here. What's the range? The range was more complicated, right? This one not so bad because this is range is all real numbers, right? The red function is going to go down forever and up forever, and the blue function the same. So the range is still y is all real numbers. Intervals of increase, intervals of decrease, zeros, minimums, maximums. Our textbook asks us for these things without sometimes asking us to graph. I think as soon as we get the graph, all this stuff is easy. So intervals of increase and decrease, it increases on, well, all numbers in the domain, in fact. We don't want to include 0 because it's not defined from 0, but then it goes to infinity. Notice here I use set notation, here I'm using interval notation, and you should be able to talk about both. Decreases, when does it decrease? When is this green function going downhill? Decreases never. It's never decreasing. What are the zeros? Well, this is actually this is the whole lesson today. So I'm going to estimate. There it is right there. There's a 0 right there. I'm going to say x-intercept a 0. eyeball it here. It looks like an x. It's not x equals a half, though, right? We said at x equals a half, it was actually a half minus 2. This was at minus a half, so it's a little more than a half. I might say x is about 0.6 maybe, and that's a guess. We don't know. That's not a very good estimate. Minimums and maximums. Well, this graph has no turning points. It's always increasing. So does it have a minimum or a maximum? No. No minimums, no maximums. And that's it for the stuff. All right, dandy. What are we doing today? Solving unsolvable. Ooh, look at that. The homework's there already. Wow. Is this the only example? Oh, no. There's some homework there. I don't want to get ahead of myself. But this is the only homework question. And in fact, we solved it already. But I want to talk about how it's actually unsolvable and how we actually just solved it. So if we try to solve this, right, when we talked at length, many chapters on how we solve inequality. So how do we solve an inequality? We're going to solve the related equation. The related equation, though, is equal to 0. How do I solve this? Well, we might say, okay, I need to get rid of log so I can get at the x. So I want to do exponential function base 2 of both sides, but that's got to go over there first because it's getting in the way. And then I do this and I go exponential function base 2 on both sides at 2. Okay, fine, 2. And then now I got this thing is canceled here, and I'm left with x equals 2 to the exponent x. Now, how do I solve this? Well, I might want to take the log of both sides to get the unknown out of the exponent, and then I go back and forth forever. Well, what's going on? Why can't I do this? Well, the idea here is we've got some techniques for solving log equations. We've got some techniques for solving polynomial equations, but not for both. There's no algebraic way to solve this. Well, didn't we do stuff like this yesterday or the day before? That was when it was a product, remember. Products are great to solve because I can bust it into its pieces. I could bust this into a logarithmic piece and a polynomial piece, and all was good. I could handle that. But this one, we are stuck. So does that mean there's no solution? Does that mean there's no solution? No. In fact, if I look back at the graph, for what values is this graph above 0? I see from here to the right, it's greater than 0. All of these values of the graph, from here over, I'm going to have solutions. Right? So I'm going to say method 1 is use a graph. And we graphed the left-hand side. The right-hand side is just the x-axis. So when is that green graph greater than 0? From the graph, because I had to state what my x-intercept was there. I'm going to say the solution appears to be greater than 0. Where is it greater than 0? The solution set is 0.6 is well, hang on, I'm mixing my my notation. I could say it's this 0.6 infinity, or in set notation x is greater than 0.6, right? Now, how confident in this solution am I? Well, not very confident. Not very confident because, you know, I just kind of I guessed at the graph. So even though this is a solution, this method 1 here is a solution, this isn't very accurate. Not very accurate. Well, let's try solution number 2. Solution number 2 you might think about, well, how close to the solution is 0.6? And that technique of saying, well, Restall said 0.6. Maybe we should just try and see how close we are. Right? Well, hang on. What was it? It was log base 2 of x plus x, and see how close to 0 we actually are. And then so I'll get out my graphing calculator or my scientific calculator rather, and I go log of 0.6 divided by, remember, change of base term, divided by log 2, right, log base 2, plus 0.6, and what do I get? So that's negative 0. What was that? Where'd it go? 0.14. So what does that mean? Well, when I put 0.6 in, I was still negative. So where should my next guess be? Well, my next guess should be a little bit to the right. Let's get bigger. This is too low. I'm looking for 0, right? So try a little bit more, maybe 0.7. What's nice, I don't want to do that, I want to go back to here. What's nice in my graphing calculator is, or your scientific calculator, you can just go back and change your guesses. And in fact, the folks that are really good with these calculators, you can actually have a whole table of guesses if you wanted to. 0.18. 0.18. So what does that mean? It means at 0.7, I'm a little bit positive. I'm on this side somewhere. 0.7 is too high. So what does this mean? It means that my answer is somewhere in the middle. So what will I try? I'll try somewhere in the middle, 0.65. And go back to my calculator. This is called the guess and improve strategy. It's not just guess and check. I want to guess and improve. That's what the textbook calls it. And isn't that nice? Guess and improve. Okay, hang on. 6.5, delete. Say, okay, Mr. Restall, we're going to be here all day. And yep, we are. We're going to be here all day doing this. I'm going to be pounding in numbers until I'm completely exact, right? Well, at some point, you're going to get satisfied that you're close enough. Usually you say within 2 decimal places or something like that. So right now, is this 0.65? Is it too high or too low? Well, this one was negative. This one's positive. 0 is somewhere in this range. So I'm going to go, and it looks like it's going to be closer to 0.65. So maybe I'll try 0.64. And then I can go back. And yes, we're going to be here all day. No, we're not going to be here all day, because at some point you get a little bit tired of doing this, and you quit. 0, 3, 8, 5. You say, well, at some point, so the answer, the answer, not the answer, the x-intercept is in the range somewhere, and not the range, the interval. I should choose my words more carefully here. The interval 0.64 to 0, and this one, between this one and the next positive one here, right? Somewhere in this interval. And so I might try 645 next. Well, when am I going to quit? I'm going to quit soon. You're probably expecting me to say, okay, here's the way that we'll get it exactly. The lesson to be learned here is you don't get it exactly. This is almost as good as we can do. Guess and improve strategy. But we will see that we've got some other tools at our disposal, and we will do that in part 2.